Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is subsection 5.2.9. Matrices represent module maps. Okay, so in the last subsection, we were kind of dealing with solving congruences and things like that. And actually, everything was kind of stemming from this idea of free Z module and making choices of for a map. And let's kind of look back at what we were doing. We were coming here. We were making choices for this map to make this well-defined. Really, we could send E1 and E2 to anything we wanted, and we'd have a well-defined map, a Z module map. So that actually motivates how to talk about and how to notate Z module maps and R module maps generally between free modules, because it really only depends where the basis elements are sent. So for instance, let's suppose okay, so let's suppose that we have a function f, and we want to send maybe we want to send, it looks like we want to send E1 to something, and we want to send E2 to something. So F is a map that goes from Z2, so Z cross Z, to Z mod 7Z. So in here, the domain is a free module. And that's really all we need here. So if the domain is a free module, then we're free to make a map here however we choose by just choosing destinations of E1 and E2. Really, it only depends on, we only need that the domain be a free module, and we can have this determination. So the basis elements are free to go wherever we want. That's one of the reasons why we call it a free module. So E1 would go, so let's just say E1 goes to one bar and E2 goes to 2 bar. That should make a nice Z module map all of a sudden, because we just found out what those destinations are. Okay, then okay, so then what about f of 3, 5? Where would that go? Well, f of 3, 5 is the same as f of 3, 1 plus 5 times E2. Then using Z module magic, we can pop things out of the f's here, outside multiplication and the addition, and use our definitions of 1 bar and 2 bar, and end up getting this. So that's great. So there's a notation that we can use for the map f. So we can kind of line up. We can line up what our images are for E1 and E2, so like image of E1, image of E2. Where does E1 go? Where does E2 go? We just write this, and this right here is notation for what f is. F is a map from a free Z module, and we can just use that notation. 1 bar, 2 bar. We can just use this in place of the function f. Okay, so f is just that. Okay, it's kind of like a matrix of sorts, but it's only a row matrix, where we're just writing out what the images of E1 and E2 are in order. And that's basically it. Okay, so now how can we talk about how to use that map or this function if that's the notation? So this is what we do. Suppose that we want to put 3, 5, which is a domain element, into this function. Well, the function, the outputs we write as a row, but the inputs we write as a column. So 3, 5 write as a column. And then we can say, okay, f of 3, 5 is, here's the row of images of E1 and E2. Here's the inputs, 3 and 5. So what's the output? Well, what we do is we just use the Z module magic, this 3 and this 5. So think of this as think of this 3 as being as simply being like 3, 1, and this 5 is being like 5 E2. So basically this E1 is going to turn into this 1 bar. See that? This E1 is because it's like you're adding these two guys to get this or pair of 3, 5. And so you can quite literally just replace this E1 by 1 bar, this E2 with 2 bar, which is what their images are, add and get this. Another way of thinking about this is you take this and you multiply it to that, then you add that to this multiplied to that. So if you've seen dot products before, it looks the same, or even matrix multiplication, it looks the same. So this times this plus that times that. Essentially, that's all we're doing, and we're just writing it notationally. So that's a notation that we can use for a module map, or that comes from a free Z module in its domain. Okay. So there's a matrix notation for this in general, and it's exactly what we said. Now this is beefed up a little bit more into a bigger matrix. How does this work? Well, this works if it's a map between two free modules. So if the domain is just free, then it's going to be a row looking like this. Now, what about the codomain? If the codomain is free, actually, so the codomain images can actually be represented as tuples then, all of a sudden, like if it's like z to the m, so that each codomain image can be written as tuples. So this is the image of E1, image of E2, image of E3, and so forth. Let's look, and plugging in has a similar notation here. So since the domain is always in a free, it's always going to, you can always write it as a tuple, and you write it down here as a column. But even in the outputs, we're listing things like image of E1, E2, E3, and so forth, but we can think of these as columns as well. The image of E1 is written as column notation, and so forth. If the codomain actually happens to be free as well. So let's look at an example when they're both free here, like this one. What does this mean? So this is a map that goes from Z3 to Z2. Now, how could you see that just by looking at this matrix? Well, because we have an image of E1, an image of E2, an image of E3. Hey, that must have meant that we had an E1, E2, and E3 in the domain, right? Which meant that the domain was Z3. So if you count the number of columns, that gives you the domain. You can call this domain dimension, or it's actually domain rank here in this particular case for free Z modules. So a rank of 3, or 3 kind of in the tuple here for the codomain, and for the domain. So the domain has a rank of 3. And what about the codomain? The codomain would have a rank of 2. Why? Because the output is expressible as a 2 tuple. So the inputs are 3 tuples because we had 3 columns from the E1, E2, and E3 that had to go somewhere. But the outputs of each one of those happen to be written as just pairs or 2 tuples. So that must have meant that we were heading to Z2 in our codomain. So how do we read this map in this function? So this means that E1 goes here, E2 goes here, E3 goes here. And what if we're inputting this? Because notice that we have the input has 3 things in it. We have 3 columns because, okay, that was the input here. So the domain is in Z3. So that's why this column has 3 things in it. That's why these columns have 2 things in it, because they're columns in the codomain, and this is a column in the domain. So the tuples written as columns. Okay, now how do we read it? Well, simply we can think the outcome of this map is, so remember what this input means, and let's write it out just to remember what it means. This input of 1, 4, and 5, this means 1 times E1 plus 4 times E2 plus 5 times E3. So if you run the module map, really, it means you're just replacing the E1 by its image, the E2 by its image, the E3 by its image, which is exactly what we have here, which amounts to just multiplication. So 1 times this column, 4 times that column, 5 times that column. See, 1 times that column, because that column is the image of E1. This column is the image of E2. This column right here is the image of E3. So then we multiply those in. So kind of what we're doing is we're taking this 1, 4, and 5 and taking them to outside multiplication, like outside multiplication of 1 to E1, outside multiplication of 4 to E2, outside multiplication of 5 to E3, and that outside multiplication continues on and stays there when we go to the codomain, and then we have the images of the codomain popping out, and we can multiply through and add. And doing that, we end up getting the result. We just add up those columns here. So we have 1 times, so literally we can go 1 times 2 plus 4 times 3 plus 5 times 4. Okay, so which is 2 plus 12, which is 14 plus 20, so 34. So we have 34 on the top, and then on the bottom we have 1 times 1 plus 4 times 3 times 4 times 0, a plus 4 times 0, just doing component wise like this if we want, which would be 1 plus 12, so 13 plus 0, so 13. Okay, so that's the result, which you could think of quite literally as, if you're familiar with matrix multiplication, you take a row and a column and you take like a dot product type thing, like 2 times 1 plus 3 times 4 plus 4 times 5. And that's going to be the first entry. Then the second entry is just 1 times 1, 3 times 4, 0 times 5, 13. So this is really where matrix multiplication comes from. It comes from representations of free Z module maps, so maps between free Z modules, or free R modules, where R is any ring. Oftentimes that ring is maybe the real numbers or something like that for matrix multiplication more generally. But it kind of plays with the same basic idea. Okay, so and with that, we'll conclude this section. There's a couple other notes in here, but that was kind of the main bit that that was most important to cover. Thanks for watching.